Okay, in this video, we're going to go over resistors in series and parallel circuits. So it's our first real dive into building circuits. So one of the things we're going to do is we're going to talk about what a series and parallel circuit is, and then we'll talk about applying that directly to resistors. So first, series circuits, and we'll talk about equivalent resistance, which is a really important concept for us to be able to kind of map out and puzzle out circuits and find various various values in the circuit, like current and voltage drops and all these kinds of things. So we'll do that for both parallel and series circuits. The lesson goals then are to differentiate series and parallel circuits. So we're going to define them both and make sure you understand the difference between them. And I'll give you a couple little, I don't know, fun facts or whatever, things to know about series and parallel circuits. And then we'll introduce the equations for finding equivalent resistance in those. Before we get into this, there's a lot that we could talk about with series and parallel circuits. I'm going to be choosing activities and questions for us to look at in class that should kind of pull those out more naturally than if I tried to explain them all. So it's really important that you pay attention to kind of the core principles of these circuits from this video. So jumping into series circuits, basically all of the elements are lined up in a series. So here, this one you can see that since we're just barely starting here, this symbol, that is some sort of a battery or maybe just some sort of voltage source. And then each of these guys here, you didn't change colors. All right, each of these guys here, these are all resistors. That's what that symbol means when you see them. And there are some other symbols you may see. At some point, I'll link a document for you guys to see all the different circuit stuff that you might see. But so the first thing that defines a series circuit is that all the elements flow from one to the other. So I have a completely straight, unbroken circuit here where there's no other branches for current to flow through. It's got to flow through all of them. And what that means is that if I look at the current through this circuit, it's going to be the same throughout the entire circuit. I have no branches where the current could maybe split. So a first fundamental principle that you have to know about series circuits is that the current is constant through the circuit. So the current through this resistor is going to be the same as the current through this resistor is going to be the same as the current through this resistor. It's the same in all of them. A consequence of that, though, is that does mean that the voltage is going to vary. So I will always kind of make sure that we say this as I start talking about these. The first thing to say is that voltage varies, and the current is constant. Those are the two really key things that you have to know about series circuits. Now, the current's got to stay the same because whatever charge is moving and flowing, it's going to be flowing at the same rate. You know, sometimes people will talk, it's not a great analogy. It's got a lot of limits and flaws, but I think it's helpful here. If you imagine current as water flowing through a pipe, well, we kind of already saw that the flow rate in a pipe has to stay the same, and current is essentially the analogous quantity for circuits. So that flow rate, the current, has to stay the same throughout this entire pipe. Now, if the pipe branched, I could see the current change in each of those, but this is one continuous flowing series circuit, so the current's going to stay the same. Now, on the other hand, whatever happens around this circuit, I know I'm starting at some sort of a positive potential and I'm ending at some negative potential. And so I have basically got to, if I kind of establish this as my 0 and this is a positive 12 volts or whatever it happens to be, as I go through these resistors, each time I go through a resistor, I'm going to experience a voltage drop across the resistor. And those voltage drops are going to have to go from 12 all the way down to 0, right? So for example, if I say this battery is 12 volts, maybe this first one I'm going to drop, well, let's say they're all the same, right? So if I drop across this resistor, I'll go 4 volts. I drop across that resistor 4 volts and that resistor 4 volts. So as I go around, I end up dropping 12 all the way back down to kind of the ground state. So two important things. The voltage drops for each resistor will vary, but the current is going to remain constant. Now, let's look at using that to try and find some sort of an equation, because one of the things that we do a lot is basically we want to say, okay, this big block of junk here, what if I could treat that as one resistor? It's a really useful tool for lots of things that may not be readily apparent, but it's extremely useful. So what if I could treat that as one resistor? We would say that that one resistor must have kind of an equivalent resistance. And so one of the first things we want to do is try and calculate how to do that. Now I'm going to use these principles that we've talked about to derive an equation that we can use for that. So I'm going to come off over here to the side, and I'm going to start with saying that the total voltage of the battery, the voltage of the battery, has got to be equal to the voltage drops of each of those resistors. And let's say we've got up to n resistors, so tons and tons of resistors. Well, each of those, I'm going to have to drop the same voltage. Now, for each of those, I could use Ohm's law, V equals IR. That's a good friend of ours. I'm going to use Ohm's law to then say that over here, that voltage for the circuit is going to be equal to the current through the circuit multiplied by what we would call the equivalent resistance of the circuit. And then over here, each of these individually is going to be equal to that same current, because the current's constant all the way through, multiplied by the resistance of 1, same current resistance of 2, so on and so forth, same current resistance of n. And now if you've been around physics a bit, and you guys all have, you may see exactly where this is going. Well, if I were to divide both sides by this current and then distribute that division to every term all the way through n terms, all those currents would cancel out, and I would end up with an expression that the equivalent resistance it's just equal to the sum of all of the individual resistances. So that is how I could find the equivalent resistance of a series circuit. Quite straightforward. So let's go over here and take a look at that. So down on this next slide, I've got it written in two different ways. So the first one is basically what I showed you that I worked out. That is kind of the simplest writing, but you guys are advanced in math, and so you may be okay with using a sigma notation, and this is what's on your formula sheet. That's why I've included it here. It's your formula sheet version. And all this is saying is that for all elements I, I'm going to add up the resistance for each element. So it's just taking the sum of all of the elements together. It just means this up here above. So that's series circuits. They're really simple and easy to work with, and we will dig in more to those in class. Now, parallel circuits are a little bit different, and so what parallel circuits are is they're circuits that are going to have separate branches. So if you see here and you looked at kind of how the current flows, so I'd have current coming out here over here. Well, what's going to happen is the current is actually going to split across these three branches. And so I'm going to end up with, if this is kind of like the current through the battery, we'll call it, what I'm going to end up with is that I'm going to have three different currents coming up down through here. So because it splits, I'm going to get different currents there. And that's a little bit different. The flip side, though, is that because all of these resistors, because these wires, they have no resistance, so all of these resistors are essentially hooked up directly to the battery. And so that means that in this case, the voltage drops for all of them are going to be the same. They're all going to be exactly the voltage drop of the battery. So all of these guys, as they go across the resistors, they're all going to drop, say, again, if I say it's a 12-volt battery, they're all going to drop 12 volts. So 12 volts there, 12 volts there, 12 volts there. They're all going to drop the same voltage because they're essentially, for all intents and purposes, connected directly to the battery on both ends. So that's one of the interesting things with parallel circuits, this kind of flips everything on its head from what we saw before. So here what we're seeing is that voltage is now going to be what stays constant amongst the elements, and instead we're going to see that current is going to vary. Now, if we look at the circuit a little bit and just talk about kind of conservation of charge and conservation of energy, well, voltage being constant takes care of conservation of charge or conservation of energy. As far as conservation of charge goes, again, we can use the analogy of water flowing through a pipe. Well, if water flows through this pipe and splits into 3 different pipes, well, all 3 of these are going to have to add up to kind of that current through the battery. And so that's important to remember. It's going to be really important for our derivation in a moment, that the current through each of the branches has to add up to whatever was supplied by the battery. One of the things that I think is interesting and maybe important to talk about is one of the strengths of parallel circuits is this. If I go back up here to my series circuit, let's say that right here between these 2 elements, I break the circuit. Well, then the current can't flow at all through any of the elements, so the whole circuit dies if I break it. If instead you think of a parallel circuit, well, if I decide I'm going to put a break in, right here, well, there's still 2 pathways for current to flow, and so these two elements, they'll keep going, they'll keep working. There'll still be a complete circuit for current to flow through down both of those branches. This branch will just be cut off. And this is a classic example of kind of like old school versus new Christmas lights. So like old school Christmas lights were a huge pain because they were wired in series. And so if a light bulb burnt out, it would break the entire circuit, right? And that would ruin everything. Now most modern light bulbs or Christmas light circuits, they're going to be wired in parallel so that if one bulb burns out, the whole strand doesn't burn out, and you can kind of more easily find the burnt out bulb. Little side note. Now, let's take a look at finding that expression for the equivalent resistance. That's going to be really useful for us down the road, and we're going to rely on these 2 ideas, the voltage being constant and the current varying. So I'm going to start with that idea that the current has to add up to kind of the current through the battery, we'll call it. So I'm going to have the current of element 1 plus the current through element 2 plus all the way up to the current through some nth element. Well, what's interesting here is I have my old friend, Ohm's law, and it's not really useful the way it's written here, but I can rewrite it to say that current is going to be equal to voltage over resistance. And so over here on this side, I'm going to replace the current through the battery with the voltage of the battery divided by that kind of equivalent resistance of the entire circuit. And here each of these is going to be replaced with voltage divided by the resistance of that element. And remember, the voltage stayed constant, so all these V's are the same. So as I add these up, I get this expression here. Now, I've got a whole bunch of V's that are all the same. So just like before, I could go ahead and I could say, well, let's just divide both sides by V, and that division gets distributed. And so I'm going to end up with that the equivalent resistance, really 1 over the equivalent resistance, is equal to 1 over resistor 1 plus 1 over resistor 2 plus all the way up to 1 over resistor N. Now, this is not as easy an equation to work with. So we saw this one up here. It's just a simple sum. This one is not as easy to work with at all. And in fact, it can be quite cumbersome for people to deal with. Note first that we've got 1 over the equivalent resistance, not the equivalent resistance. Most people leave it written this way. If you really wanted to, you could probably go ahead and write it this way to say that the equivalent resistance, if I take the inverse of both sides, I could make it 1 over R1 plus 1 over R2 plus all the way up to 1 over Rn. That's a bit yucky to write, and nobody really likes that. But you can do that. I do think this expression here in red can be useful if you have some questions that are kind of trying to dig into the concepts of like, well, what happens if I change the resistance of this element, or what happens if I take this light bulb out? What happens to the other elements? So it can be really useful to think of it this way. Now let's go look at how it's on your formula chart. So again, here's how I like to write it. The 1 over the parallel is equal to 1 over R1 plus 1 over R2 plus blah, 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 blah. And they use this sigma notation again. So it's just saying for I elements, you're going to add them all up. 1 over R1 plus 1 over R2 plus 1 over it means this, right? It's the exact same thing, just written in a different style. And that's really all I wanted to try and cover for this video. So just to recap just a little bit, I'll try not to go overboard here. First, series circuits are where all the elements flow in one direction. And the important thing here is that voltage is going to vary. So the voltage is going to drop over all of these, and those drops have to add up to the voltage source. And the current, though, is going to remain constant throughout that entire branch because of our conservation of charge. When we do all of our funky math over here, we eventually arrive with this equivalent resistance being just the sum of all the resistors. It's quite straightforward. Parallel circuits, we've got elements in branches, and so what we see here is because they're all essentially hooked up straight to the battery, the voltage is the same in every branch, and instead the current is what's going to vary. And that's because if you imagine this current flowing and splitting down 3 paths, those 3 are going to have to add up to the total current before, but they are going to be different. And here we can see, again, our equations for finding the equivalent resistance. It's a bit of a pain of an equation, but it's really not too bad once you start using it. So let's make sure we talked about our lesson goals here. First, we differentiated series and parallel circuits, and we also introduced those equations for finding equivalent resistance in series and parallel by kind of deriving them. There's a lot more we're going to do with this, but I think that that's going to be best seen by you guys just kind of playing with it and seeing how it all comes out. I think I could make an hour-and-a-half long video talking about all the different things, but it's just not going to be as valuable as letting you guys do it. So that's what we'll be doing in class.